Delaware Tech, Chemistry 100, Chemistry 110, Colligative properties. Colligative properties are properties that depend only on the number of dissolved particles, that is the concentration of the solution, and not on what the particles are. In other words, it doesn't matter what solute is dissolved, it only matters how many particles of the solute are actually in solution. So they're bulk properties that change when you put solute in solvent. And there are 4 of these properties that will change that are dependent only on how much solute is dissolved in the solvent and not on what the solute is. Vapor pressure will actually go down if you dissolve more solute in solution. So in other words, it's harder to vaporize. The vapor pressure will be depressed or lowered because it's harder to make that solvent turn into vapor. Freezing point depression. This is because it's harder to freeze, and we'll talk about that as well. Boiling point elevation, because it's harder to boil. And osmotic pressure will be elevated, and we haven't talked about osmotic pressure. That'll be in the next module. But osmotic pressure is a pressure that results from water trying to go through a membrane to dilute a more concentrated side of the membrane. And this pressure will go up if you have more solute dissolved. So it's harder to purify pure water from salty or sugary or whatever water that has something dissolved in it. And that is called osmotic pressure elevation. So let's look at these. So colligative properties are bulk properties. They're only based on how much solute is dissolved, not what the solute is. And electrolytes become very important because electrolytes are solutes that will break up into ions when they go in solution. So we only care about how many particles. We don't care about how many formula units of an ionic compound we throw in. We care about how many ions it becomes when it goes into solution, specifically when it goes into water. So let's look at some of these types of ionic compounds. These formula units, NaCl, sodium chloride. When you put this in water, 1 NaCl will become 1 Na plus, a sodium ion, and 1 Cl minus, a chloride ion. So you'll get 2 particles for every 1 that you think you're throwing in the water. If we threw in calcium fluoride, we would get 3, 1 calcium ion and 2 fluoride ions. We throw in chromium 3 sulfate. This is a very soluble compound. It will completely break up into its component ions, and you will end up with 2 chromium 3 ions and 3 sulfate ions for a total of 5 particles for every 1 of these formula units. Glucose, however, is not an ionic compound. It's a covalent compound, so when you put it in water, it just stays as glucose, C6H12O6. It doesn't break apart. It's not ionic. And therefore, you'll get 1 for 1. Every molecule of glucose you throw in that dissolves, it will be 1 particle dissolved. And this number of particles per formula or formula unit is called the Vant Hoff factor, and it's abbreviated as I. That's the symbol. So if you have a certain concentration of sodium chloride or calcium fluoride, etc., you have to multiply it by the I value to tell you really the concentration of how many particles total you actually have in solution. In other words, the effective concentration. So we're concerned more about the effective concentration because colligative properties depend only on the concentration of these non-volatile solute particles, typically solid solutes that we're talking about here. So we don't care what the identity of the compound is except to tell us how many particles it will break up into. In other words, to tell us the value of I, the Vant Hoff factor. So the effective concentration is just the concentration times the I, times the Vant Hoff factor, how many particles per molecule or per formula unit. For example, if I have a 0.1 molar NaCl solution that I made, in other words, I took a tenth of a mole of sodium chloride and dissolved it in 1 liter, that would be a 0.1 molar solution. However, there's 0.1 molar of the sodium ions and there's 0.1 molar of the chloride ions. So that's a total of 0.2 molar of particles. We don't care about the fact that they're different particles. We only care about the total concentration. Likewise, magnesium nitrate, a very soluble compound, breaks up into a total of 3 ions, 1 magnesium ion, 2 nitrates. So if I make a 0.1 molar solution of magnesium nitrate, I really have 0.3 molar of particles dissolved in that solution. Likewise, if I have tungsten 5 sulfate, this will break up into 2 tungsten 5 ions and 5 sulfate ions for a total of 7 particles for each formula unit. So if I make a 0.1 molar solution, I really have 0.7 molar of particles in solution. And sucrose, like most sugars, is a covalent compound. And therefore, if I make 0.1 molar sucrose, well, it's still 0.1 molar because the sucrose does not break into individual particles. It's a covalent molecule, so it just stays as a whole molecule when it's dissolved. So let's look at the individual colligative properties. First one, vapor pressure lowering. So if you add a non-volatile solute, like a solid, to a solution, like water, to a solvent like water, the water vapor pressure will go down. And you might be wondering, well, why is that? Well, the vapor pressure of the non-volatile component, that is the solid, is 0. Solids don't make vapors usually. So if I threw sodium chloride in the water, the sodium chloride doesn't add any new vapors. You won't get vapors of sodium chloride, but you'll get vapors of water coming off of that. Now, the interesting thing here is, once you put more sodium chloride in solution, or whatever it is you're dissolving in your aqueous solution, you just have less water, and because there's more of the other thing. If you have more solute, you have less solvent, and therefore there's less solvent to become vapor. So the vapor pressure only goes down because there's less solvent to produce vapor. It's as simple as that. So the solution's vapor pressure is dependent on the solute concentration, and the unit of concentration for this particular measurement is the mole fraction, and we don't discuss that much in Chem 100. In fact, we don't talk about that at all. So just understand that that's a unit of concentration. So if the concentration of the solute is down, the vapor pressure will be high. If the solute concentration is up, there's less solvent to produce vapor, so the vapor pressure will be lowered. So the second colligative property we'll look at here is freezing point depression. And what this says is that when you add more solute to the solvent, the freezing point of the solution will go down. So here is a phase diagram. You've seen simplified versions of these, and I'm going to highlight this for what you did see before. So this is a plot of pressure versus temperature, and we have solids, liquids, and gases appearing in different parts of this diagram. So you saw a version that only had one set of curves, and I'm going to overrun the green part here with a thicker green so that you can see this is what the original curve was. And in this particular curve, this portion was our solid, this portion was our liquid, and this portion was our gas. So in this, you'll notice solids are at low temperature, gases are at high temperature and low pressure, and liquids are somewhere in the middle, that kind of Goldilocks area between temperatures of the solid and the gas. And we have these transitions, so if we just focus on one pressure, so we're only looking at along this line right here. So we only care about this. This is what we're exposed to every day at 1 atmosphere pressure. We're not going to look at the rest of the phase diagram for just yet, but I want you to see that this point here represents where solids transition to liquids. In other words, that temperature where that transition happens, and I'm going to use a different color so you can see this a little bit better, right there is our melting point. That's our melting point at 1 atmosphere pressure. And if we look over on the other side of this point here would be our boiling point. This is where we're transitioning from liquid to gas across this line right here at 1 atmosphere pressure. So that's our boiling point right there, that temperature that's represented on our x-axis. Well, what happens when you add solute to the solvent is the freezing point will go down. It'll actually move, and you'll end up with this whole new phase diagram shown here in kind of a blue-purple, you'll notice the boiling point goes up as well in this curve, and we're going to talk about that in the very next slide. But what happens is you add more solvent, it makes it harder to freeze, so the freezing point goes down. It also makes it harder to boil, so the boiling point goes up. So I'm going to clear those notes because it's a little cluttered here. So this will only work until you reach saturation. In other words, I add more and more salt or sugar or whatever it is I'm dissolving the water. The freezing point will keep going down and down and down, and eventually I won't be able to put any more in solution. I'll reach saturation, and the freezing point won't go any lower, but I'll hit some limit. So examples of this: salting a road in winter. We put salt on the roads to keep the ice from staying frozen. We are literally lowering the freezing point of water by putting salt on the ice. So suddenly, ice that would be frozen at, say, 0 degrees centigrade would no longer be frozen. It would turn back into water. And the more ice you throw on it, the lower you make the freezing point, the harder you make it to freeze. And therefore, you can melt more and more snow. Antifreeze in winter. We put antifreeze in our radiator in our car in order to make the water harder to freeze in cold weather. You don't want the water freezing, otherwise it can't flow through your engine and cool off your engine. So we add ethylene glycol, that's the main component of antifreeze. This is a liquid solute that makes the freezing point go down tremendously, actually. Now, I already mentioned that boiling point will also be increased when we add salt. So if you add more non-volatile solute, in other words, a solvent or a liquid that doesn't vaporize, to your solution, the boiling point will go up. And we also have the freezing point going down. So you get this new curve, as I showed before, this blue-purple curve, which is our new phase diagram with a different transition between solid and liquid and between liquid and gas. And this is related to the fact that the vapor pressure has been lowered. If you remember our first colligative property, vapor pressure depression, because there's less solvent available to vaporize, it's harder to make vapor. Well, if it's harder to make vapor, it's harder to completely evaporate, and we call that process boiling. So lowering of the vapor pressure and raising of the boiling point are really manifestations of the same phenomena. There's just less material to boil or to vaporize, and therefore it's harder. And again, this will only work until you reach saturation. Once you can't dissolve any more sugar or salt or whatever you're dissolving, you can't make the boiling point go up any higher. So examples of this: we put salt in our water when we cook pasta, and that makes the boiling point get higher. What that means is the water will not boil until it's a hotter temperature, and that means you get to cook your pasta at a higher temperature than you normally would cook it if it was just pure water. Of course, we also add salt because it flavors the pasta. Antifreeze, we put it in the winter, but we also have it in the car in the summer. It does the same thing to help with the boiling as it does with the freezing. It makes it harder to freeze, but it also makes it harder to boil. And as a result, in hot weather in the summer, your engine will not, the radiator water will not boil up and overheat, preventing your engine from overheating. So it keeps liquid water flowing around your hot engine, and that way it pulls off heat and keeps your engine cool so that you can keep running your car. So remember, adding more solute to water or to any solvent makes it harder to freeze, freezing point goes down, and harder to boil, boiling point goes up, and the vapor pressure goes down.